All right, guys, welcome to another episode of Cuda Education. Uh, Today, I want to talk about a couple of things. We're going to tackle the shader binding table. All right, so let's tackle the shader binding table. All right, and we are going to use well, first of all, this is Cuda Education. And we're going to use the raytracingshadows.cpp algorithm as sort of so ray tracing shadows as our algorithm. All right, so basically what I want to do is really tackle I really want to tackle the I really want to tackle the shader binding table and how it relates to everything in our algorithm. It's sort of been a sticking point for me, and yeah. So the best way, it's gonna be involved, but I'm trying to make it as quick as possible. So we have an algorithm, ray tracing shadows, that basically shoots rays into a scene. We have objects on a platform, and we have a light source circling the platform and the object on the platform. And the object casts a shadow on the platform, and we have shadows. And we have the primary rays coming in from the camera, hitting the object, and then we do a shadow test from the point of impact to the light source to see whether the shadow test or the shadow ray makes it to the light source, or it doesn't make it to the light source because it has been intersected by a what you might call it, has been intersected by an object between the point of contact, the hit point, and the light source. All right. Let me just make sure that everything is set up properly. All right, so to start off the fun, we have a CPU section over here. I'll just put it over here. So we have the CPU over here. And of course, you guys know the CPU is your the CPU is your regular processor on your machine. It's not the GPU. And on the CPU we have we have a command called VKCMD trace raise KHR. So I'm just gonna put it down here. Maybe I'll put it in a different color. So we have a command called lowercase vk cmd trace raise KHR. All right. So this command is what sort of initiates the cascade that we're about to witness. All right. This VK ray trace KHR. It's a very important function. This is, you know, it's in the raytracingshadows.cpp, you know, C++ script, and it's what starts off everything. Now, just as a sanity check, I left the whole application just the way it is. And this is in the previous video. I left the whole application just the way it is, but I commented out or removed VKCMD trace raise KHR. When I do that, when I remove VKCMD trace raise KHR, that call, the application runs, we get a window, and you know, we get our little menu in the upper left hand corner, but as far as what you see in the window, it's completely blank. All right. So that's an important test, because number one, it shows that, okay, without this function call, everything else still runs. There's no crash, there's no build time errors, there's no compilation errors, nothing like that, right? When you remove this one function, the whole application is blanked out, but the application runs, right? So it's just an important thing to understand, that this function is what drives everything else. All right, and this is on the Vulkan API. This is what initiates everything that we see in the application. But it's important to start with this function because we're going to get into other stuff. And I just wanted to make sure that is very clear. So we have our CPU. And as far as the CPU is concerned, I'm going to leave this. I'm going to leave this the way it is for right now. Now, you know, I'm messing with these colors, so just bear with me, guys. I'm messing with all these colors and stuff, but I'm trying to do it so that you guys can follow. All right. So we have our CPU, and then we have our GPU, and I'm generally going to put it over here, but we kind of have to be you know, you kind of have to follow what I'm trying to do. So we have over here, we have our GPU, right? And I'm just going to put it all the way up here. GPU. And specifically, what we care about is the what they call the traversal hardware. Okay. And basically it's what is in charge of the part of the GPU that's in charge of like taking rays and traversing it across the scene. Okay. So, you know, just keep that in mind. That's the GPU side, right? I would normally do like a line between the two, but I kind of need to have this area, general area to sort of discuss some things. We're gonna mess around with some colors today, guys. So let me try. We got okay. We're just gonna do. So we have green for the GPU. Okay, so we have our VKCMD trace raise KHR, which fires off everything that we basically are gonna see going forward, right? And that's from the Vulkan API. That's a Vulkan function. You know, anything with a lowercase VK, we know that it's super important in Vulkan land. Okay. So now let us I'm going to do a I'm going to do a huge box, right? That basically goes all the way around like this, and we're going to call this host visible memory. Okay, so what host visible memory is that whatever memory or whatever things we're doing on the GPU, it's accessible and readable from the CPU side. So we have our CPU over here, and we have our GPU over here, and we have host visible memory. All right. So everything in this container is sort of the host visible memory. And then we just we continue with this you know, with this approach. So we have host visible memory, we have and then I'll just even do a different color again. So we have host visible memory, and then we have match green. I'll just do blue. All right, so we have host visible memory, and then we have our shader binding table, right? And then within the shader binding table, we have our what I call SBT, shader binding table handles. And within our shader binding table handles, we have our SBT regions. And within our shader binding table regions, we have different regions. So we have We have a region, and then within the region we have a shader group. And within the shader group, we have the region shader. All right, so we have our region. Then we have our shader group. And then we have our region shader. All right. So that's all for the region. We have maybe I'll do it up here. We have a miss region. We have a shader group. We have a miss shader, and we have a shadow. Wait. We have a shadow miss shader. All right, so let me see how I'm gonna draw this. I need a wide kind of berth for this one. All right, so we'll do miss shader. We have the shader group. Oh, I guess I could spell it out. We have our shadow miss shader and we have our miss shader and our shadow miss shader. All right, so we have our region, our shader group, and our region shader. We have our miss region, our shader group, and our miss shader and our shadow miss shader. We have talked about this in previous videos. You know, I'll get to that more in another you know, in a second. All right, and then we have our hit region, shader group, and our hit shader. Okay, so for what it's worth, all right, so we have so we have our hit region, our shader group, and our hit shader. All right, and then, you know, for all intents and purposes, there's a callable region, but I'm not going to put that on there just for lack of space. All right. Now, technically, the shader binding table lives on the GPU, and all of these elements live on the GPU in GPU memory. Okay. But remember that I say host visible memory. So host visible memory, this means that both the GPU and the CPU can see it, can update it, can put things in there, can read it, all that good stuff, right? But technically, all of this stuff lives in the GPU. Now the thing is that all of this information here is all of this information here is filled in by all of this information is filled in by the all of this information is filled in by the CPU. Okay, so you know the CPU does all the reason why it has to be host visible is because the CPU fills in. So CPU. So the CPU fills all data into shader binding table. All right. So yeah, it gets messy with this one, but all right. So all of the information in here is being filled in by the CPU, okay? But the GPU is going to use this information. So that's pretty much that story right there. Now, just do a quick sanity check. Okay, so we have our shader binding table that basically organizes all the things that the GPU is going to need for scene traversal, right? So we're traversing the scene with rays. All right. So let us do a hard so let us just do a hard line right here. All right. Okay. So now I'd rather do a very strong. All right. So we have our camera, and I gotta be very concise with this. So we have our camera, right? This is the camera, right? We have our camera here. We have a light source. Right? We have our camera, we have our light source. We have our platform, right? So we'll do the platform. We'll do the platform right here. Make a bigger platform. So we have our platform right here, and then we have our hammer. So the hammer is sort of, no, I don't like that. The hammer is sort of like this, okay? So we have a ray that shoots from the camera and hits the actual object. Okay? What part of the shader binding table is activated with this? So what part of the shader binding table is activated with that hit? Well, that is going to activate the hit shader. So that is going to activate the hit shader because we now have a hit. In the hit shader, remember we then have a call in the hit shader called where is it? Trace ray ext. All right, trace ray ext. So this trace ray ext, I'll do it a little better. All right, so this trace ray ext, this trace ray ext is what activates the shadow test. The shadow test ray. Okay. So this activates now the shadow test ray. So from here, basically from this point to this point, we activate the shadow test ray, right? And this guy is because of this. So trace ray ext in the hit shader activates the shadow test ray, or the shadow ray. Now, in this case, what's being activated? So we now do a shadow test ray, and we see that there's no obstruction between the object and the light source. So because there is no obstruction with that, what gets activated is this. So basically there is no obstruction between the object that was hit, the point at which the object was hit, and the light source. So what gets activated here is this guy, right? And basically what we're saying is that this point is lit. So this point is illuminated. It's shown. It's being shown in the scene. Now, if you don't know, by default, the application starts out with assuming that everything is shadowed, right? So basically, we do these light tests. So this is a primary ray. Primary ray. And this is a shadow ray. Shadow ray. Okay? So everything is assumed to be shadowed unless you do a test and you realize that you have no obstructions to the light. So because of that, this shadow miss shader is activated, and basically what it does is it turns off the shadowing. So now this point is lit. All right. Now we do have as the shadow yeah, I messed this up. So let's say this is the shadow, right? This is basically behind the object, right? So at this point, we're gonna have a hit, but you're going to see that the shadow test ray fails here. So this stays shaded because the shadow test ray fails, because instead of it going to the light source, it Maybe I should do it a little bit more. All right, so we have, so let's say it's right here. And then we try to get to the light source, but it fails because the object is blocking. So because it fails, we don't do anything. We don't activate any shaders or anything like that. We just leave it shadowed, right? Because remember, everything by default is assumed to be shadowed, so we don't have to deal with that. Now we also have a ray that basically doesn't go anywhere. Like, it doesn't hit anything, it's not activated. This now is going to be dealt with by, I don't even want to, it's going to be dealt with by the mist shader, right? So the mist shader, I think in our example, the background color of the thing is blue, so we get a blue background, right? And that's pretty much it. The ray generation is actually ray generation. We are generating rays, right? These two are rays, so this is also trace ray EXT. Okay, so we're generating rays here and we're generating rays here. Okay, trace ray EXT. So these guys are all raygen, right? These two are raygen. So this is raygen. I don't want to confuse it, but this is raygen. So I'll just do raygen shader, right? Raygen shader, right? And this is hit shader. So whenever I see a ray generated, you know there's trace ray EXT. All right. So that's basically it, guys. One thing you have to understand is that trace ray EXT is a GLSL function. It is something that lives and is initiated by in shaders. You need to have the ray tracing extension activated in the shader. So in the raygen shader and the hit shader, the ray tracing extension is activated in those shaders. And in the previous video, I show you where the raygen shaders, the ray tracing extensions are activated. This is the reason why I always say, if you want to run the ray tracing examples, you need to make sure your GPU has ray tracing capabilities, because if you, like, I've tried to comment out the ray tracing extension requirement in these shaders, and when I do that and try to compile them to spare V format, it doesn't compile, right? There's an error and all that stuff, and the reason is because of this trace ray EXT. So yes, Vulkan deals with firing off all of this stuff, right? Vulkan deals with firing off with VKCMD trace rays KHR. But when it comes to actually dealing with the application and stuff, it's this trace ray EXT that micromanages everything and and does all the generating the rays and all that stuff. Again, if I erase this function call in raytracingshadows.cpp, if I erase this function call, nothing here happens. Like you don't see anything on your screen, you just get a blank screen, right? So you could set up all the shader binding table and do everything you want from the CPU and have your code nice and whatever, but if you don't call this bad boy, nothing happens. And obviously, if you take out traceray.ext and these shaders, I believe nothing happens. I have to check again, but I believe like nothing happens, right? You don't see anything because you're not generating any rays anywhere. I don't think it crashes, but you're not seeing anything if you remove the traceray.ext. And that shader binding table for you. It was a little bit, abstract for me up until this point, but now I kind of understand, how they encapsulate it and maybe even why they do it. Now, there may be more complicated considerations as to why they have it this way, but I could run with this. I could understand this. The other thing that I wanted to quickly mention is that they, in ray tracing and in the discussion of ray tracing, Vulkan ray tracing, they talk about these acceleration structures. Everything is accelerated, and you need these acceleration structures. The acceleration structures are basically the bounding volume hierarchy boxes that I've previously discussed. So, like for this particular situation, you would have an imaginary box around the hammer, and let's say you had a bunch of items lined up here, right? You just have one box around all of the items, and then if as the ray is traversing the scene, it never touches the box, or it never intersects the box, or it never hits the box, then it can be assumed that all the objects in that box has not been hit, right? And it's sort of an efficiency shortcut. So it helps to cut down on compute times, because then if you know that you did hit the box, then you don't have to search for every item within that box, every object within that box to see if you hit it, because you didn't hit the bounding volume hierarchy box. So therefore you you could cut out processing for all the other objects, and that's like a compute shortcut. And that's what basically acceleration structures are, right? It's a way to help the traversal hardware and your application and the processing to make sure that you don't have you don't process stuff unnecessarily. That is my contribution for today. The SBT handles has something to do with like drivers and stuff, and making it easy for the GPU to access. Because remember, every pixel on your monitor, every pixel in the application has to go through this process, right? So it's literally every pixel that you see on your screen, right? And every pixel that you see on your screen is going to be, is it shadowed or is it lit? Is it shadowed or is it lit, right? If you do a hit here and you do the shadow test and it's a clear thing to, or here and you do a shadow test and it's a clear thing to the light source, then you know that this part of the platform, all of these parts of the platform is lit, because there's a clear at these points there's a clear line of sight to the light source. So you have your SBT shader binding table regions, you have the handles, and you have the shader binding table. Now, this is all in host visible memory. There are other ways of doing it, but I just ran with the host visible memory version. Notice that in the miss region, you have two shaders. So in the hit region, you just have one hit shader and you have one ray gen shader. But in the miss region, you have a miss shader and you have a shadow miss shader, right? So the miss shader is just the sky model, the background color, and then the shadow miss shader is whether you're going to turn on and off the shadowed portion For this case, you're turning off the shadowed thing because everything by default is considered shadowed until you turn it off. So all of these places you're going to be hitting the shadow mesh shader because you're turning off the shadowed portion, right? The platform and the object itself and whatever. Now only this area you wouldn't necessarily be you wouldn't necessarily be you wouldn't necessarily be hitting the shadow mesh shader because it stays off, right? For this area right here. And that's it, guys. That's your CPU, your GPU, your shader binding table, your RayGen shader. So all of these is the RayGen shader, and this is the hit shader right here that launches the shadow test ray, trace ray XD, trace ray XD, VKCMD, trace rays KHR. All right, guys. Tutorial number 1 to install the Vulkan API on your Windows-based machine with a Vulkan-capable GPU. Tutorial number 13 is for a whole host of examples, including this one. In order for you to run this particular example and the ray tracing examples in the whole list of examples, you need to make sure your GPU is ray tracing capable. If it's NVIDIA you're running, it has to be RTX or later or greater. For the other vendors, Intel and AMD, I have no idea. But for NVIDIA, you need to have the RTX card. All right, so we've learned something today. Thank you for watching. Have a great day.